Imagine a world where the oceans have vanished, where the continents lie cracked and barren beneath a sky thick with suffocating heat, where the sun, once our gentle companion, has become an executioner. This is Earth 1 billion years from now, a scorched, unrecognizable wasteland where even the hardiest microbes struggle to survive. The transformation won't happen overnight. It will unfold across hundreds of millions of years, driven by forces so vast and inexorable that nothing on this planet can stop them. And it all begins with something we take for granted every single day: the steady, brilliant light of our sun. If you enjoyed learning about our planet's distant future, make sure to hit that like button and subscribe to the channel for more explorations of the cosmos. Your support helps us continue bringing you fascinating science content like this. What will set Earth on this path of destruction? The answer lies not in asteroids or supervolcanoes, but in the very star that gave us life. Our sun is aging, and as it ages, it's getting brighter. Right now, at this very moment, the sun is converting hydrogen into helium deep within its core through nuclear fusion. This process has been happening for over 4.5 billion years. But there's a catch. Helium is heavier than hydrogen. So as more and more helium accumulates in the sun's core, that core becomes denser. It contracts under its own weight. And when it contracts, gravitational potential energy is released as heat. That extra heat increases the temperature and pressure in the core, which accelerates the rate of fusion. More fusion means more energy output. More energy output means the sun gets brighter. It's a slow process, imperceptible across human lifetimes. But zoom out to cosmic timescales, and the pattern becomes clear. The sun is increasing its brightness by about 10% every billion years. That might not sound like much, but for a planet like Earth, finely balanced within a narrow habitable zone, that 10% makes all the difference. 500 million years from now, the sun will be roughly 5% brighter than it is today. That additional energy will warm the surface of the Earth. It will speed up chemical reactions in the atmosphere and oceans, and it will trigger a cascade of changes that, once begun, cannot be reversed. To understand what happens next, we need to talk about something called the carbonate-silicate cycle. This is Earth's natural thermostat, a planetary feedback loop that has kept our climate stable for billions of years. Here's how it works. When volcanoes erupt, they release carbon dioxide into the atmosphere. That carbon dioxide dissolves in water vapor, forming a weak acid called carbonic acid. This acidic water falls as rain. When it hits the ground, it reacts with silicate minerals in rocks, breaking them down in a process called chemical weathering. The products of this weathering, calcium ions and bicarbonate ions, get washed into rivers and streams. They flow down to the oceans. There, marine organisms use these dissolved ions to build shells and skeletons made of calcium carbonate. When those organisms die, their shells sink to the ocean floor and eventually get buried. Over millions of years, the ocean crust carrying these carbonate rocks gets pulled down into the mantle at subduction zones. Deep underground, intense heat and pressure break the carbonates back down, releasing carbon dioxide. That carbon dioxide rises back up through the crust and erupts from volcanoes, completing the cycle. This cycle is beautifully self-regulating. If carbon dioxide levels rise, the planet warms. Warmer temperatures increase rainfall and speed up chemical weathering. More weathering pulls more carbon dioxide out of the atmosphere, cooling the planet back down. If carbon dioxide levels drop, the planet cools. Cooler temperatures slow down weathering. Volcanic outgassing continues. Carbon dioxide builds back up, and the planet warms again. For billions of years, this negative feedback loop has kept Earth's temperature within a range where liquid water can exist. It's the reason our planet didn't freeze solid when the sun was dimmer in the distant past. And it's the reason we didn't boil away as the sun gradually brightened. But 500 million years from now, something changes. The brightening sun pushes this delicate system past a tipping point. The extra heat accelerates chemical weathering faster than volcanic outgassing can replace the carbon dioxide. Atmospheric carbon dioxide levels start to plummet, and when carbon dioxide drops, plants are in trouble. Plants need carbon dioxide to photosynthesize. It's their primary source of carbon, the building block of all the organic molecules that make up their cells. Different types of plants have different minimum carbon dioxide requirements. Trees and most flowering plants, which use what's called C3 photosynthesis, need relatively high carbon dioxide levels. Grasses and certain other plants, which use C4 photosynthesis, can survive with less, but there's a hard flaw. Below a certain concentration of carbon dioxide in the atmosphere, photosynthesis becomes impossible. The planet's carbon dioxide levels will eventually drop below the threshold required for C3 plants. Forests will begin to die. The great rainforests that once covered vast stretches of the continents will wither and disappear. Grasslands, which are more resilient, will hold on for a while longer, but even they won't last forever. As the sun continues to brighten and carbon dioxide continues to drop, C4 plants will also succumb. The age of complex plant life on Earth will come to an end, not because of an asteroid impact, not because of a supervolcano, but because the very air they breathe will no longer sustain them. The collapse of the plant kingdom will trigger a domino effect that ripples through the entire biosphere. Without plants, there is no food for herbivores. Deer, elephants, insects that feed on leaves and grasses will starve. Their populations will crash. And when the herbivores go, so do the carnivores. Lions, wolves, eagles, all the predators that depend on herbivores for food will have nothing left to hunt. The great megafauna, the large animals that once roamed the plains and forests, will be among the first to go. They require enormous amounts of food to sustain their massive bodies. Smaller animals might last a bit longer, scavenging on the remnants of the dying ecosystem, but eventually, they too will disappear. The oceans won't be spared either. Phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web, also need carbon dioxide. As atmospheric levels drop, so does the dissolved carbon dioxide in seawater. Phytoplankton populations will decline. The fish, whales, and countless other marine creatures that depend on them will starve. Coral reefs, already stressed by warming waters, will bleach and die. The vibrant underwater cities of life that took millions of years to build will crumble into barren skeletal remains. Within a few million years of plants disappearing, most complex animal life on Earth will be gone. The age of multicellular organisms, which began over 600 million years ago during the Cambrian explosion, will end. The planet will belong once again to simpler forms of life. Bacteria and archaea, the ancient microbes that dominated Earth for its first 3 billion years, will be all that's left. But even the microbes won't have an easy time of it, because as the sun keeps getting brighter, the heat becomes unbearable. 700 million years from now, the sun's luminosity will have increased by about 7%. Surface temperatures on Earth will be noticeably higher than they are today. The polar ice caps, if any still exist, will be melting. The climate zones will be shifting. Regions that were once temperate will become scorching deserts. Rainfall patterns will change. Some areas will experience intense droughts. Others will be battered by violent storms as the atmosphere tries to redistribute the excess heat. The planet's water cycle will be in overdrive. With higher temperatures, more water evaporates from the oceans and lakes. Water vapor is a powerful greenhouse gas, even more potent than carbon dioxide. So as more water enters the atmosphere, it traps even more heat. This creates a feedback loop. More heat causes more evaporation. More evaporation causes more heat. The oceans are still there at this point. They're warmer and they're slowly shrinking, but they haven't vanished. Not yet. The real crisis is still to come. 800 million years from now, the sun is 8% brighter. The effects are accelerating. The oceans are visibly lower. Coastal regions that were once underwater are now exposed. Ancient shipwrecks lie on dry land, their hulls baking under the relentless sun. The remaining water is warmer and saltier. Marine life, already decimated, clings to survival in the few remaining cool pockets near the poles. On land, the vegetation is long gone. The continents are vast deserts. Sand dunes stretch for hundreds of kilometers. Dry riverbeds carve through the landscape, remnants of a time when water flowed freely. The only life that remains is microbial. Extremophiles, bacteria, and archaea that have evolved to survive in the harshest conditions, hide in the few places where moisture still lingers. Underground caves, cracks in rocks, high-altitude mountains where temperatures are slightly cooler, they're the planet's last holdouts. 900 million years from now, the sun is 9% brighter. The oceans have lost nearly a quarter of their volume. Subduction, the process where oceanic crust is pulled down into the mantle, is starting to slow. Without enough water to lubricate the boundaries between tectonic plates, the plates don't slide as easily. Volcanic activity begins to decline. Fewer volcanoes mean less carbon dioxide being released into the atmosphere. But it doesn't matter anymore. The plant life that once depended on carbon dioxide is long gone. The planet's tectonic engine, which has been running for billions of years, is winding down. And then we hit 1 billion years. 1 billion years from now, the sun is 10% brighter than it is today. This is the threshold. This is the point where Earth enters what scientists call the moist greenhouse phase. The surface temperature has climbed to the point where the atmosphere becomes saturated with water vapor. Think of it like this. On Earth today, the amount of water vapor in the air is limited by temperature. When air gets too saturated, the excess water condenses out as rain or snow. But when the entire planet is hot enough, water vapor doesn't condense. It just stays in the atmosphere, building up. And because water vapor is such a powerful greenhouse gas, it traps enormous amounts of heat. The temperature climbs even higher. More water evaporates. More water vapor enters the atmosphere. The cycle becomes a runaway feedback loop. At this point, the oceans are evaporating faster than rainfall can replace them. The water cycle as we know it is breaking down. Rain still falls, but it's not enough. The oceans are shrinking rapidly now. Within a few 100 million years, they'll be gone entirely. Where does all that water go? Some of it stays in the atmosphere as vapor, but much of it escapes into space. Here's how. Water molecules in the upper atmosphere are bombarded by high-energy ultraviolet light from the sun. That ultraviolet light splits the water molecules apart, breaking the bonds between hydrogen and oxygen. The hydrogen, being the lightest element, drifts up and away, escaping Earth's gravity entirely. The oxygen either gets stripped away by the solar wind or reacts with rocks on the surface, forming oxides. Over millions of years, Earth bleeds its water into space. The blue planet becomes a brown planet. By 1.2 billion years from now, the oceans are mostly gone. What's left are a few shallow seas in the deepest basins. Salt flats stretch across the old ocean floors, vast expanses of white crust where seawater once evaporated, leaving behind layers of salt. The atmosphere is thick and oppressive, choked with water vapor and whatever carbon dioxide is still being outgassed from the dying remnants of volcanic activity. Surface temperatures are climbing toward 50 degrees Celsius, even in regions that were once temperate. At the equator, it's even hotter. Daytime temperatures can reach 70 degrees Celsius or more. This is a planet in its death throes. The continents are still moving though. Plate tectonics hasn't completely stopped yet. The land masses are slowly drifting toward each other, driven by forces deep within the mantle. In about 250 million years from this point, they'll collide and merge into a new supercontinent. Let's call it Pangaea Proxima, as some geologists have suggested. But this supercontinent won't look anything like the lush, vibrant Pangaea of the past. It will be a barren wasteland. The interior of the continent, far from any remaining water, will be a scorching desert. Temperatures could reach 55 degrees Celsius or higher. The only habitable regions, if you can even call them that, will be near the poles, where it's slightly cooler. And even there, life will be nearly impossible. The formation of this supercontinent will disrupt ocean currents even further. The few remaining seas will lose their oxygen below a certain depth. Deep water will become stagnant and lifeless. Marine life, already on its last legs, will face another mass extinction. The only organisms left will be extremophiles, microbes that can tolerate extreme heat, high salinity, and low oxygen. They'll huddle in the last pockets of moisture, in underground aquifers, in ice caves at high altitudes, in the cracks of rocks where morning dew might briefly condense before evaporating again. But the sun keeps getting brighter. 1.5 billion years from now, it's 15% brighter than today. Surface temperatures are soaring. Even the poles are too hot for most life. The atmosphere is a thick soup of water vapor, carbon dioxide and nitrogen. The pressure is increasing as more and more water vapor accumulates. The surface is becoming a pressure cooker. The remaining water is almost entirely in the atmosphere now. There might be a few isolated pools in deep craters or high mountain valleys, but they won't last. The heat is relentless. The ultraviolet radiation from the sun is more intense than ever. Without an ozone layer, which has been destroyed by the changing atmospheric chemistry, nothing is shielded from the sun's harsh light. Any microbe trying to survive on the surface would be fried by radiation. The only safe havens are underground. Deep caves, where the temperature is buffered by the surrounding rock. Cracks in the crust where ice might still be trapped. These are the final refuges. And even here, life is barely hanging on. 2 billion years from now, the sun is 20% brighter. Earth is unrecognizable. The oceans are completely gone. Every drop of water that once filled the vast basins has either been baked into the atmosphere or lost to space. The surface is a baked, cracked desert. The old ocean floors are now dry plains covered in salt deposits. The continents are riddled with impact craters, because without oceans and a thick atmosphere to shield it, Earth is being bombarded by asteroids and comets. Each impact leaves a scar, a reminder of the violence of the cosmos. Volcanic activity has mostly ceased. Without water to lubricate the tectonic plates, Subduction has ground to a halt. The plates are locked in place. The planet's internal heat is still there, slowly radiating away, but it's not enough to drive the massive convection currents that once powered plate tectonics. Without active volcanism, there's no fresh carbon dioxide being released. The atmosphere is dominated by nitrogen and whatever carbon dioxide has built up over the eons. The greenhouse effect is extreme. Surface temperatures are over 100 degrees Celsius. In some places, they might reach 150 degrees Celsius. This is hotter than the boiling point of water at sea level. If any liquid water were to somehow appear on the surface, it would boil away instantly. The last microbes are deep underground, in pockets of ice that have been protected from the heat. They're in a state of dormancy, barely clinging to existence. They're not thriving. They're just surviving. Waiting. For what? It's hard to say. There's no rescue coming. The planet is dying. 2.8 billion years from now, the sun is nearly 28% brighter. This is the end of complex life. Surface temperatures, even at the poles, have reached 149 degrees Celsius. At this temperature, proteins denature. Cell membranes break down. DNA unravels. No known organism can survive. The last of the extremophiles, the microbes that have endured through all the previous catastrophes, finally succumb to the heat. They die, and with them, all life on Earth is extinguished. The planet is now biologically dead. If an alien spacecraft were to fly past at this moment, scanning for signs of life, they would find nothing. No oxygen in the atmosphere to indicate photosynthesis. No methane to suggest biological activity. No complex organic molecules. Just a hot, barren rock orbiting a brightening star. They would have no idea that this world was once teeming with life. That it was home to forests and oceans, to dinosaurs and humans, to countless species that lived and died over billions of years. All of that is gone, erased by the relentless march of time and the inevitable evolution of the sun. But the story doesn't end there. The planet itself will continue to change. 3 billion years from now, the sun is over 30% brighter. Earth's surface is a hellscape. The atmosphere is thick and heavy, dominated by carbon dioxide and nitrogen. Water vapor is still present, but it's trapped in the upper atmosphere, unable to condense. The pressure at the surface is immense. The temperature is over 200 degrees Celsius. The ground is baked hard, almost like ceramic. Any remaining volatiles, chemicals that would normally evaporate at lower temperatures, are being cooked out of the rocks. The planet is slowly degassing, releasing whatever gases are left in the crust. The surface is dry and cracked. Vast plains of basalt, the cooled remnants of ancient lava flows, stretch across the continents. In some places, there are towering shield volcanoes, remnants of the last gasps of geological activity. These volcanoes are dormant now, their magma chambers long since cooled, but they stand as monuments to a more active past. 4 billion years from now, the sun is 40% brighter. Earth is experiencing a runaway greenhouse effect, similar to what happened on Venus billions of years ago. The temperature at the surface is climbing toward 400 degrees Celsius. The atmosphere is incredibly dense, with surface pressures many times higher than Earth's current atmospheric pressure. The heat is so intense that the surface rocks are starting to glow. In some places, the rock is beginning to melt. Lava pools are forming, not from volcanic activity, but from the sheer heat of the sun. The planet is on the verge of becoming a molten world. The continents, once solid and stable, are starting to soften. The crust is beginning to flow like a very thick liquid. This is the beginning of the end for Earth's solid surface. Over the next few billion years, more and more of the crust will melt. The planet will become a global ocean of lava, with only a few floating islands of solid rock remaining. 5 billion years from now, the sun is 50% brighter. But now, something else is happening. The sun is running out of hydrogen in its core. For billions of years, it's been fusing hydrogen into helium, and that process has kept it stable. But now, the hydrogen in the core is nearly depleted. When the last of the hydrogen is used up, fusion in the core will stop. And when fusion stops, there's no outward pressure to counteract gravity. The core will start to collapse. As the core collapses, it heats up. That heat ignites hydrogen fusion in a shell around the core. The energy from this shell fusion pushes the outer layers of the sun outward. The sun begins to expand. It's entering the subgiant phase of its evolution. The sun's surface cools slightly, shifting from yellow to a more orange hue. But even though the surface is cooler, the sun's overall luminosity is increasing because it's getting so much bigger. The amount of energy hitting Earth is skyrocketing. 6 billion years from now, the sun is over 100 times brighter than it was when Earth first formed. It has swollen into a red giant. The sun's outer layers now extend far beyond its original size. Mercury, the innermost planet, has already been engulfed. It's gone, vaporized in the searing heat. Venus is next. The sun's surface is creeping closer and closer to Venus's orbit. Earth is still there, but it's barely recognizable. The surface temperature is over 1,000 degrees Celsius. The crust has completely melted. The planet is a globe of molten rock, glowing red hot. The atmosphere, if you can even call it that anymore, is a thin veil of vaporized metals and silicate gases. The oceans, the continents, the mountains, the valleys, all of it has been reduced to a churning sea of lava. And the sun keeps expanding. The question is, will Earth be swallowed too? For a long time, scientists debated this. Some models suggested that as the sun loses mass during its red giant phase, its gravitational pull on the planets would weaken. Earth's orbit would expand, moving it outward, potentially saving it from being engulfed. But recent observations of other stars in the galaxy have given us a clearer picture. And the news isn't good. Studies using data from NASA's Transiting Exoplanet Survey satellite have found that red giants devour their inner planets far more often than we thought. Out of hundreds of planetary systems observed, very few inner planets remain around red giants. Most of them have been swallowed. Earth will likely suffer the same fate. As the sun continues to expand, its outer layers will reach Earth's orbit. The planet will find itself inside the sun's outer atmosphere. The friction will cause Earth's orbit to decay. It will spiral inward, closer and closer to the sun's core. The heat will be unimaginable. The surface of the planet, already molten, will begin to vaporize. Chunks of the crust will boil away into space. The planet will disintegrate piece by piece until there's nothing left but a cloud of gas and dust. 7.5 billion years from now, Earth is gone, completely consumed by the sun. The planet that was once a blue marble, teeming with life, is now nothing more than vapor dispersed throughout the sun's expanding envelope. The sun itself won't last much longer in this state. The helium that's been accumulating in the core will eventually ignite. Helium fusion is more energetic than hydrogen fusion. The core will heat up to an astonishing 100 million degrees Celsius. The sudden surge of energy will cause the sun to expand even further, briefly becoming even brighter. But this phase won't last. Helium fusion is short-lived. Within a few 100 million years, The helium in the core will be exhausted. Fusion will stop again. The core will collapse one final time, but it won't have enough mass to ignite carbon fusion. The Sun isn't massive enough for that. Instead, the core will settle into a stable, ultra-dense state called a white dwarf. The outer layers, no longer supported by fusion, will be puffed off into space, forming a beautiful planetary nebula. The white dwarf at the center will be all that remains of our Sun, a glowing ember slowly cooling over trillions of years. The solar system, or what's left of it, will be a very different place. Mercury and Venus are gone, consumed by the Sun. Earth is gone. Mars, the fourth planet, might have survived, though it would have been scorched by the expanding Sun. Its surface would be baked and lifeless. The outer planets, Jupiter, Saturn, Uranus, and Neptune, would have drifted outward as the Sun lost mass. They would still be there, orbiting the white dwarf, frozen and dark. Their moons, once potential havens for life, would be icy tombs. The asteroid belt would be mostly intact, a collection of rocky debris orbiting silently in the void. And far out in the Kuiper belt, trillions of icy comets would continue their slow dance around the dying star. The solar system would be a graveyard, a monument to the life and death of a star. But it wouldn't be the end of everything. The material ejected by the Sun during its red giant phase, the gas and dust from the planetary nebula, would drift out into space. Over millions of years, it would mix with other clouds of gas and dust in the galaxy, and eventually, some of that material would collapse under its own gravity, forming a new star. That new star might have planets. Those planets might have conditions suitable for life. The atoms that once made up Earth, the carbon and oxygen and nitrogen that were part of living organisms, would be recycled. They would become part of new worlds. The cycle of birth, life, and death would continue. This is the story of Earth 1 billion years from now and beyond. It's a story of transformation, of destruction, of the inevitable march of entropy. But it's also a story of resilience, because even though Earth will be gone, the legacy of life on this planet will live on in the atoms that scatter across the galaxy. Now, before we close, let's take a step back and think about what all of this means for us. I mentioned at the beginning that we're assuming no human intervention in any of this, but that's a big assumption. Humans have already demonstrated an incredible ability to shape the world around us. We've altered the climate. We've engineered ecosystems. We've even started to venture beyond our planet. If humanity survives for the next few 100,000 years, let alone the next few million, there's a good chance we'll find ways to adapt to these changes. We might develop technologies to regulate Earth's climate, to replenish the oceans, to sequester carbon dioxide from the atmosphere. We might build habitats underground or in space, places where we can survive even as the surface becomes uninhabitable. We might even find a way to move Earth itself, nudging its orbit outward to keep it in the habitable zone as the Sun brightens. It sounds like science fiction, but so did flying to the moon 100 years ago. Or we might leave. We might colonize other planets, moons, even other star systems. Mars could be terraformed. The moons of Jupiter and Saturn, like Europa and Enceladus, which have subsurface oceans, could be made habitable. We could build generation ships, massive spacecraft that travel between the stars, carrying humanity to new worlds. The point is, the end of Earth doesn't have to be the end of us. But even if it is, even if humanity doesn't survive to see the Sun become a red giant, that's okay. Everything has a lifespan. Stars are born, they live and they die. planets form, they evolve, and eventually they're destroyed. Life appears, it flourishes, and then it fades away. This is the natural order of the universe, and there's a certain beauty in that. Earth's story, from its formation 4.5 billion years ago to its eventual destruction billions of years in the future, is a reminder that nothing lasts forever. But it's also a reminder that the time we have is precious. Right now, in this moment, Earth is alive. It's vibrant and beautiful and teeming with life. We're part of that story. We get to experience this incredible planet in its prime, in the age of oceans and forests, of biodiversity and complexity. That's a gift, and it's a responsibility, because the future of life on Earth, at least in the near term, is in our hands. The choices we make today about how we treat the environment, about how we use our resources, about how we interact with the other species we share this planet with, those choices matter. They won't change what happens billions of years from now, but they will determine what kind of world we leave for the generations that come after us. So let's take care of this planet while we still can. Let's appreciate the beauty of a world with oceans and blue skies. Let's protect the incredible diversity of life that makes Earth so special. Because one day, billions of years from now, it will all be gone. But until then, this is our home, and it's worth fighting for. As we look ahead to Earth's distant future, it's important to understand the specific mechanisms that will drive these changes. Let's dive deeper into the science of how our planet's climate system will unravel. The carbonate-silicate cycle, which we touched on earlier, deserves a closer look because it's central to understanding why Earth will ultimately fail to maintain its habitability. This cycle has been operating for billions of years, and it's the reason Earth managed to stay habitable even when the sun was significantly dimmer in the past. The young sun, about 4.5 billion years ago, was roughly 30% less luminous than it is today. By all rights, Earth should have been a frozen ice ball. But it wasn't. Geological evidence shows that liquid water existed on the surface even back then. How? The answer is higher concentrations of carbon dioxide in the atmosphere. With more carbon dioxide, the greenhouse effect was stronger, compensating for the weaker sun. As the sun gradually brightened over billions of years, the carbonate-silicate cycle drew down atmospheric carbon dioxide, keeping the temperature stable. But this system has its limits. The weathering process depends on liquid water. Rain falls on rocks, reacts with them, and carries the weathering products to the ocean. As the sun gets brighter and temperatures rise, the rate of this chemical weathering increases. At first, this is a good thing. It pulls excess carbon dioxide out of the atmosphere, preventing runaway warming. But as the process accelerates, it starts pulling out more carbon dioxide than volcanic outgassing can replace. Volcanic activity is the primary source of carbon dioxide returning to the atmosphere. Volcanoes erupt when tectonic plates collide or spread apart, and when subducted rocks are heated deep in the mantle. But the rate of volcanic outgassing is relatively stable over long timescales. It's controlled by the heat flow from Earth's interior and the rate of plate tectonics. So while weathering can speed up dramatically in response to higher temperatures, volcanic outgassing can't keep pace. The result is a net loss of atmospheric carbon dioxide. And once carbon dioxide drops below a critical threshold, plants can no longer photosynthesize effectively. For C3 plants, which include most trees and many crops, that threshold is around 150 parts per million. For C4 plants, which include many grasses, the threshold is lower, around 10 parts per million. But eventually, even C4 plants will run out of carbon dioxide When that happens, the planet's primary producers, the organisms that form the base of the food web, disappear, and the entire ecosystem collapses. The timeline for this collapse depends on several factors. How quickly does the sun brighten? How efficiently does the carbonate-silicate cycle pull carbon dioxide out of the atmosphere? How much carbon dioxide is stored in reservoirs like the ocean and the crust? And how quickly can it be released? Different models give slightly different answers, but the consensus is that complex plant life will start to decline somewhere between 500 million and 800 million years from now. By 1 billion years, it will be mostly gone. And once the plants are gone, the rest of the biosphere follows within a few tens of millions of years. Let's examine the specific mechanisms that will lead to the decline of different types of plants. Not all plants are created equal when it comes to their carbon dioxide requirements. We need to understand the difference between C3 and C4 photosynthesis. C3 photosynthesis is the most common form, used by about 95% of plant species, including most trees, shrubs, and many crops like wheat and rice. In C3 photosynthesis, the plant captures carbon dioxide through tiny pores called stomata and immediately incorporates it into a 3-carbon molecule. This process works well when carbon dioxide levels are relatively high, but it becomes inefficient when carbon dioxide is scarce. That's because the enzyme responsible for capturing carbon dioxide, called rubisco, sometimes grabs oxygen instead of carbon dioxide, leading to a wasteful process called photorespiration. When atmospheric carbon dioxide drops below about 150 parts per million, C3 plants struggle to photosynthesize efficiently. They spend more energy dealing with photorespiration than they gain from photosynthesis. They stop growing. They become weak and vulnerable to disease and pests. And eventually, they die. C4 photosynthesis is a more advanced system that evolved in response to low carbon dioxide environments. C4 plants, which include corn, sugarcane, and many tropical grasses, have a special mechanism for concentrating carbon dioxide around the rubisco enzyme. This allows them to photosynthesize efficiently even when atmospheric carbon dioxide is very low. They can survive at carbon dioxide levels as low as 10 parts per million, far below what C3 plants need. So when the atmospheric carbon dioxide drops below 150 parts per million, C3 plants will start to disappear. The great forests will die first. Oak trees, maple trees, pine trees, all of them will wither and decay. The understory plants, the shrubs and ferns and wildflowers that grow beneath the forest canopy will follow. Grasslands, dominated by C4 plants, will expand to fill the void. For a while, the planet will look like a savanna, with scattered trees and vast expanses of grass. But this is only a temporary reprieve. As carbon dioxide continues to drop, eventually falling below 10 parts per million, even the C4 plants will succumb. The grasslands will turn brown and die, and the age of vascular plants, which began about 470 million years ago when plants first colonized the land, will come to an end. But what about non-vascular plants? Mosses, liverworts, algae. These organisms don't have the complex tissues of vascular plants, and some of them have different photosynthetic pathways. Could they survive longer? The answer is maybe, but not much longer. Mosses and liverworts also rely on photosynthesis to capture carbon dioxide, and while some species are more efficient than others, they all have limits. When atmospheric carbon dioxide drops to near zero, photosynthesis becomes impossible for all plant life. The only photosynthetic organisms that might persist a bit longer are certain types of cyanobacteria ancient photosynthetic microbes that were the first to produce oxygen on Earth billions of years ago. Some cyanobacteria have carbon-concentrating mechanisms that allow them to photosynthesize at extremely low carbon dioxide levels. They might be able to eke out an existence for a few million years after the last plants are gone, living in specialized niches where carbon dioxide is slightly more abundant. But even they will eventually fail, and when they do, photosynthesis on Earth will cease entirely. The loss of photosynthesis has cascading effects that go far beyond the obvious starvation of herbivores and carnivores. Photosynthesis is what produces the oxygen in our atmosphere. Over billions of years, photosynthetic organisms have converted carbon dioxide and water into sugars and oxygen, gradually building up atmospheric oxygen from trace amounts to the 21% we have today. But photosynthesis is a continuous process. It's not a one-time event. Oxygen is constantly being consumed by respiration, by decomposition, by weathering of rocks, by volcanic gases. The only reason atmospheric oxygen stays at 21% is because photosynthesis is constantly replenishing it. When photosynthesis stops, oxygen production stops, and oxygen levels begin to decline. The decline is gradual at first. Oxygen will react with organic matter in the soil, decomposing the remains of the dead plants and animals. It will react with iron and other metals in rocks, forming rust and other oxides. It will react with methane and other reduced gases that are released by volcanic activity. Over millions of years, these reactions will pull oxygen out of the atmosphere and lock it away in solid minerals. The exact rate of decline depends on how much reactive material is available and how much volcanic activity continues to release reduced gases. But most models suggest that within 50 to 100 million years after the end of photosynthesis, atmospheric oxygen could drop to less than 1% of its current level. For any animals that somehow manage to survive the collapse of the food web, this would be the final blow. Complex animals need oxygen to breathe. Their cells use oxygen to break down glucose and extract energy through a process called aerobic respiration. This is far more efficient than anaerobic respiration, which doesn't use oxygen but produces much less energy. Animals evolved in an oxygen-rich environment, and their bodies are optimized for aerobic respiration. When oxygen levels drop, they struggle. They become weak and lethargic. Their muscles don't work as well. Their brains, which are extremely energy-hungry organs, start to fail, and eventually they suffocate. But realistically, by the time oxygen levels drop significantly, there won't be any complex animals left. They'll already be gone, starved to death, when the plants disappeared. The oxygen decline is just the final nail in the coffin, ensuring that even if some animals somehow found a way to survive without plants, they'd still eventually die. Now let's think about what happens to the nitrogen cycle. Nitrogen is essential for life. It's a key component of amino acids, which make up proteins, and of nucleotides, which make up DNA and RNA. The atmosphere is 78% nitrogen gas, but most organisms can't use nitrogen in this gaseous form. It needs to be converted into more reactive forms, like ammonia or nitrate, through a process called nitrogen fixation. On Earth today, nitrogen fixation is carried out primarily by certain bacteria, many of which live in symbiotic relationships with plants. For example, legumes like beans and peas have nodules on their roots that house nitrogen-fixing bacteria. The bacteria convert atmospheric nitrogen into ammonia, which the plant can use, and in return, the plant provides the bacteria with sugars from photosynthesis. When plants die and decompose, the nitrogen in their tissues is released back into the soil, where it can be taken up by other plants or converted back into atmospheric nitrogen by other bacteria. This is the nitrogen cycle, and it's essential for maintaining the fertility of the soil. But when plants disappear, the nitrogen cycle is disrupted. Without plants to partner with, many nitrogen-fixing bacteria will lose their primary habitat and food source. The rate of nitrogen fixation will drop dramatically, and without plants to absorb nitrates from the soil, much of the nitrogen will be washed into rivers and eventually into the ocean. Over time, the soil will become depleted of nitrogen, making it even less hospitable to any organisms that might try to colonize it. In the oceans, the influx of nitrogen could initially cause blooms of algae and cyanobacteria, organisms that can still photosynthesize as long as carbon dioxide is available. But these blooms will be short-lived. When the algae die and decompose, the decomposition process will consume oxygen, creating dead zones in the water where nothing can survive. And as carbon dioxide levels continue to drop, even the algae and cyanobacteria will disappear, and the nitrogen cycle in the oceans will also collapse. What about the phosphorus cycle? Phosphorus is another essential element for life. It's a component of DNA, RNA, ATP, the molecule that stores energy in cells, and cell membranes. Unlike nitrogen, phosphorus doesn't have a gaseous phase. It's locked up in rocks, primarily in the form of phosphate minerals. These minerals are slowly weathered by rain and rivers, releasing dissolved phosphate into the water. Plants and microbes take up this phosphate, use it to build their cells, and when they die, the phosphate is released back into the environment. Eventually, much of the phosphate ends up in the ocean, where it's incorporated into marine organisms or precipitated into sediments. Over millions of years, these sediments can be uplifted by tectonic activity, forming new rocks, and the cycle begins again. But when plants and microbes disappear, there's nothing to take up the phosphate. It will continue to be weathered out of rocks and washed into the ocean, but it won't be recycled through living organisms. It will accumulate in ocean sediments, essentially being removed from the active ecosystem. This depletion of phosphorus in terrestrial environments will make it even harder for life to persist. Even if carbon dioxide levels somehow recovered, even if temperatures somehow stabilized, the lack of available phosphorus would prevent complex ecosystems from re-establishing. Let's also consider the sulfur cycle. Sulfur is important for life because it's a component of certain amino acids and vitamins. In the modern world, sulfur cycles through the environment in various forms. Volcanic eruptions release sulfur dioxide gas, which reacts with water in the atmosphere to form sulfuric acid, a component of acid rain. This acid rain falls on the land, where it can react with rocks or be taken up by organisms. In the oceans, certain bacteria can convert sulfate into hydrogen, sulfide, a toxic gas that smells like rotten eggs. Other bacteria can oxidize hydrogen sulfide back to sulfate. This cycling of sulfur is important for maintaining the chemistry of the environment. But when volcanic activity declines, as it will when tectonic activity slows and eventually stops, the primary source of sulfur to the atmosphere and oceans will be cut off. The sulfur cycle will wind down. And while this might seem like a small detail, it's another example of how interconnected all of these biogeochemical cycles are. When one cycle is disrupted, it affects the others. And when multiple cycles are disrupted simultaneously, the entire system collapses. Another critical factor to consider is the role of soil. Soil isn't just dirt. It's a complex mixture of minerals, organic matter, water, air, and living organisms. In healthy soil, there are billions of bacteria, fungi, insects, worms, and other organisms in every handful. These organisms play crucial roles in breaking down organic matter, recycling nutrients, and creating the structure that allows plant roots to grow. When plants disappear, the organisms that depend on them will also disappear. Fungi that form symbiotic relationships with plant roots, called mycorrhizae, will have no hosts. Earthworms that feed on decaying plant matter will have no food. The soil food web will collapse. Without living organisms to maintain it, soil will degrade. The organic matter will decompose and wash away. The structure will break down, leaving nothing but loose mineral particles. Rain will erode this degraded soil, washing it into rivers and eventually into the ocean. Over millions of years, the continents will be stripped of their soil, leaving bare rock exposed to the elements. This process, called denudation, will be accelerated by the lack of plant roots to hold the soil in place. The landscape will change dramatically. Mountains will erode more quickly. River valleys will deepen and widen, and the sediments carried by these rivers will accumulate in the oceans, burying whatever marine ecosystems might still be clinging to life. Now, let's talk about the oceans in more detail. The oceans are massive heat sinks, capable of absorbing and storing enormous amounts of thermal energy. They're also the largest reservoir of carbon dioxide on the planet. Today, the oceans contain about 50 times more carbon dioxide than the atmosphere, dissolved in the water as carbonic acid and various ionic species. As the atmosphere warms and carbon dioxide levels initially rise due to increased volcanic outgassing, some of that carbon dioxide will dissolve into the oceans. But there's a catch. Warmer water holds less dissolved gas than cold water. So as the oceans warm, they'll actually release some of their stored carbon dioxide back into the atmosphere, exacerbating the greenhouse effect. This is another positive feedback loop. More carbon dioxide in the atmosphere leads to warmer temperatures. Warmer temperatures heat the oceans. Warmer oceans release more carbon dioxide. And round it goes. Eventually, though, the carbonate-silicate cycle will pull carbon dioxide out of the atmosphere faster than the oceans can release it. Atmospheric carbon dioxide levels will drop. And as they drop, the oceans will start absorbing carbon dioxide from the atmosphere again, trying to maintain equilibrium. But the oceans can only absorb so much, and as temperatures continue to rise, the ability of the oceans to hold dissolved gases decreases. By the time we reach the moist greenhouse phase, the oceans will be so warm that they'll be releasing water vapor and carbon dioxide at an accelerating rate. The surface of the ocean will be churning and bubbling, almost like a pot of water on a stove. Evaporation will be intense. Vast clouds of steam will rise into the atmosphere, creating a thick, oppressive blanket of humidity. And beneath this blanket, the ocean will slowly shrink. The process of ocean evaporation isn't uniform. The equatorial regions, which receive the most direct sunlight, will lose water fastest. The tropical oceans will shrink and become shallower. Coral reefs, already stressed by warming and acidification, will be exposed to the air and die. The shallow seas that cover continental shelves, like the North Sea or the Gulf of Mexico, will evaporate and disappear entirely. As the oceans shrink, the remaining water will become more saline. Today, seawater has a salinity of about 3.5%, meaning that 3.5 grams of salt are dissolved in every 100 grams of water. But as water evaporates, the salt is left behind. The salinity increases. Eventually, the oceans will become hypersaline, with salinity levels exceeding 10% or even 20%. For most marine organisms, this is lethal. Fish, crustaceans, mollusks, they all have specific salinity tolerances. When the salinity rises too high, their cells can't maintain the right balance of ions. They become dehydrated and die. Only a few specialized organisms, halophilic bacteria and archaea, can survive in such extreme conditions. And these extremophiles will be the last marine life on Earth. As the oceans continue to evaporate, they'll eventually fragment into isolated seas, like the Great Salt Lake or the Dead Sea, but on a much larger scale. These hypersaline remnants will persist in the deepest ocean basins, places like the Mariana Trench or the Puerto Rico Trench. They'll be incredibly hostile environments, with temperatures exceeding 50 degrees Celsius, salinity levels higher than any modern ocean, and crushing pressures at depth. But even these remnants won't last forever. The relentless evaporation will continue, and within a few 100 million years of entering the moist greenhouse phase, even the deepest basins will be dry. The ocean floors, once covered in sediments teeming with life, will be exposed to the air for the first time in billions of years. There'll be vast plains of dried mud, cracked and fissured like the desert floor. Salt deposits, precipitated from the evaporating seawater, will form thick crusts, glittering white under the harsh sun. These salt flats will stretch for thousands of kilometers, remnants of the oceans that once covered 70% of the planet's surface. And what about the polar ice caps? Today, Earth has ice sheets covering Antarctica and Greenland, as well as seasonal sea ice in the Arctic. These ice sheets play a critical role in regulating the planet's climate. They reflect sunlight back into space, helping to keep temperatures cool. They store vast amounts of fresh water, and they drive ocean currents by releasing cold, dense water as the ice melts. But as the sun brightens and temperatures rise, the ice caps will be among the first casualties. The process is already underway, even in our current era, with global warming causing ice sheets to melt at accelerating rates. But on the timescales, we're talking about hundreds of millions of years in the future. The ice caps will be completely gone. The Arctic Ocean will be ice-free year-round. Greenland and Antarctica will be ice-free continents. The meltwater from these ice sheets will raise sea levels significantly, flooding coastal areas and creating new shallow seas. But this flooding will be temporary. As the oceans evaporate, sea levels will drop again, and those flooded areas will be exposed once more. The loss of the ice caps will have profound effects on the planet's albedo, its reflectivity. Ice and snow are highly reflective, bouncing back about 70 to 90% of the sunlight that hits them. This is why polar regions stay so cold. But when the ice melts and is replaced by open water or bare rock, the albedo drops dramatically. Water absorbs about 90% of the sunlight that hits it, and rock absorbs about 80 to 90%. This means that more solar energy is absorbed by the planet, warming it further. This is yet another positive feedback loop. Warmer temperatures melt the ice. Less ice means lower albedo. Lower albedo means more energy is absorbed. More energy means higher temperatures. And the cycle continues. These feedback loops are what make climate change so dangerous and so difficult to stop once it gets started. They amplify small changes, turning them into large runaway effects. Now, let's zoom out and think about what all of this means for the planet's energy budget. Every planet has an energy budget, a balance between the energy it receives from the sun and the energy it radiates back into space. For Earth, the incoming energy is solar, radiation, mostly in the form of visible light. This energy heats the surface and the atmosphere. The planet then radiates energy back into space in the form of infrared radiation, or heat. When the incoming energy equals the outgoing energy, the planet is in thermal equilibrium, and its temperature stays stable. But if the incoming energy increases, as it will when the sun gets brighter, the planet heats up. It has to radiate more energy to balance the budget. The problem is that the amount of energy a planet radiates depends on its temperature and its atmospheric composition. Greenhouse gases like carbon dioxide, methane, and water vapor trap infrared radiation, preventing it from escaping into space. This is the greenhouse effect, and it's what keeps Earth warm enough for liquid water and life. But when greenhouse gas levels become too high, or when the planet gets too hot, the greenhouse effect becomes too strong. The planet can't radiate enough energy to balance the incoming solar radiation. It enters a state of radiative imbalance, and its temperature keeps rising. This is what will happen to Earth as the sun brightens and the moist greenhouse phase begins. The planet will receive more and more energy from the sun. Water vapor will accumulate in the atmosphere, trapping more and more heat. The temperature will rise. The planet will try to radiate more energy by getting hotter, but the greenhouse effect will prevent most of that energy from escaping. The radiative imbalance will grow, and the temperature will spiral out of control in a runaway greenhouse effect. This is what happened to Venus. Venus is similar in size and composition to Earth, and it's thought to have had liquid water on its surface early in its history. But Venus is closer to the Sun, and it receives about twice as much solar energy as Earth. At some point in the past, probably a few billion years ago, Venus entered a moist greenhouse phase. Its oceans evaporated, water vapor accumulated in the atmosphere, and the greenhouse effect became so strong that the planet's temperature skyrocketed. Today, Venus's surface temperature is 460 degrees Celsius, hot enough to melt lead. Its atmospheric pressure is 90 times greater than Earth's, and its atmosphere is 96% carbon dioxide. It's a hellish world, utterly inhospitable to life as we know it. And it's a preview of what Earth will become. But there's one key difference between Venus and Earth. Venus is already in a stable, albeit extreme state. Its temperature is high enough that all of its water has been lost to space. There's no more runaway feedback. It's reached a new equilibrium. Earth, on the other hand, still has water. And as long as there's water, there's the potential for change. The moist greenhouse phase on Earth will last for hundreds of millions of years as the oceans gradually evaporate. During this time, the planet will be in a state of flux, constantly changing, constantly losing water, constantly getting hotter. It's a slow-motion catastrophe, playing out over timescales that are hard for us to comprehend. But it's as inevitable as the sunrise. Let's also think about the impact of solar wind and cosmic radiation during these future epochs. The sun doesn't just emit light and heat. It also emits a stream of charged particles called the solar wind. These particles flow out from the sun in all directions, filling the solar system with a tenuous plasma. Earth is protected from the solar wind by its magnetic field, which deflects the charged particles and prevents them from reaching the surface. This magnetic field is generated by the motion of molten iron in Earth's outer core, a process called the geodynamo. But the geodynamo won't last forever. It's powered by heat from the core. And as the planet cools over billions of years, the heat flow decreases. Eventually, the geodynamo will weaken and might even shut down entirely. When that happens, Earth will lose its magnetic shield. the solar wind will hit the atmosphere directly, stripping away atoms and molecules and carrying them off into space. This process is called atmospheric escape, and it's one of the ways planets lose their atmospheres over geological time. We see evidence of this on Mars. Mars once had a thicker atmosphere and possibly even a magnetic field, but it lost both billions of years ago. Today, Mars's atmosphere is only about 1% as thick as Earth's, and it's constantly being stripped away by the solar wind. Earth will eventually suffer the same fate. As the sun brightens and becomes more active during its red giant phase, the solar wind will intensify. Without a magnetic field to protect it, Earth's atmosphere will be eroded away. Nitrogen, oxygen, carbon dioxide, whatever gases are left, will be ionized by the solar wind and carried off into space. The planet will be stripped naked, left with only the thinnest whisper of an atmosphere, if any at all. And without an atmosphere to provide pressure and transport heat, the surface temperature will swing wildly between day and night. The day side facing the sun will be scorching hot. The night side facing away will be freezing cold. It will be a barren, airless rock, orbiting a dying star. In addition to the solar wind, the planet will be exposed to cosmic rays, high-energy particles from outside the solar system. Cosmic rays are mostly protons and atomic nuclei, accelerated to nearly the speed of light by supernova explosions and other violent events in the galaxy. They bombard all planets constantly, but Earth's atmosphere and magnetic field shield us from most of them. When these shields are gone, cosmic rays will hit the surface unimpeded. They'll cause intense radiation damage, breaking apart molecules, ionizing atoms, and creating secondary particles that penetrate deep into the ground. Any organic molecules that might still be present on the surface, remnants of the long-dead biosphere, will be broken down and destroyed by this radiation. Over time, the surface will become completely sterilized, devoid of any chemical traces of life. If alien archaeologists were to visit Earth billions of years in the future, they'd find no fossils, no organic compounds, no evidence that this world was once alive. It would be as if life had never existed here at all. Now, as we approach the end of the main sequence phase of the Sun's life, about 5 billion years from now, things will start to change very quickly. The Sun will have exhausted most of the hydrogen in its core. Fusion will slow and then stop. Without the outward pressure from fusion to counteract gravity, the core will begin to collapse. As it collapses, it will heat up, eventually reaching temperatures high enough to ignite hydrogen fusion in a shell surrounding the core. This shell fusion will release enormous amounts of energy, far more than the core fusion did. The outer layers of the Sun will be pushed outward by this energy. The Sun will expand. It will grow from a yellow dwarf star into a subgiant, and then into a full-fledged red giant. During this expansion, the Sun's luminosity will increase dramatically. Within a few 100 million years, it could be hundreds or even thousands of times brighter than it is today. The habitable zone, the region around a star where liquid water can exist on a planet's surface, will shift outward. Mars, frozen and barren today, will briefly become warm enough for liquid water. The moons of Jupiter and Saturn, icy worlds with subsurface oceans, will thaw. For a brief moment in cosmic time, these outer worlds will have a chance at habitability, but it will be fleeting, because the Sun's expansion won't stop there. As the Sun continues to swell, its surface will cool. The intense heat in the core and the fusion shell will push the outer layers so far out that they'll be diffuse and relatively cool. the sun's color will shift from yellow to orange to red. This is why it's called a red giant. But don't let the cooler surface fool you. The total amount of energy being radiated by the sun will be immense, far greater than it is today, and that energy will have devastating effects on the inner planets. Mercury, the closest planet to the sun, will be the first to be engulfed. As the sun's outer layers reach Mercury's orbit, the planet will find itself inside the sun. The friction with the sun's outer atmosphere will cause Mercury's orbit to decay. It will spiral inward closer and closer to the sun's core until it's torn apart and vaporized. A similar fate awaits Venus, and then, most likely, Earth. There's been some debate among astronomers about whether Earth will actually be engulfed by the sun or whether it might escape. The argument goes like this. As the sun loses mass during its red giant phase, shedding its outer layers into space through powerful stellar winds, its gravitational pull on the planets will weaken. When a star loses mass, the orbits of its planets expand. It's a consequence of orbital mechanics. Less mass means less gravity, means a larger orbit. Some calculations suggest that Earth's orbit could expand by as much as 50%, moving it from 1 astronomical unit, its current distance, to about 1.5 astronomical units. At that distance, Earth might just barely escape being engulfed by the expanding sun. But recent studies paint a different picture. Observations of other stars that have gone through the red giant phase show that inner planets rarely survive. Data from the Transiting Exoplanet Survey satellite and other telescopes have revealed that red giants tend to be devoid of close-in planets. The planets that should be there, based on what we know about planetary system formation, are missing. The most likely explanation is that they were swallowed. The sun's outer atmosphere, even though it's diffuse, still exerts drag on any object passing through it. This drag causes the planet's orbit to decay, pulling it inward. It's a process called orbital decay, and it's more powerful than the outward push from the sun's mass loss. So even if Earth's orbit initially expands, the drag from the sun's outer atmosphere will eventually pull it back in. The planet will spiral toward its doom. What will that be like? Imagine Earth, already a lifeless, molten ball of rock from billions of years of increasing solar radiation, now sinking into the sun's outer layers. The sun's outer atmosphere is thin, much less dense than Earth's atmosphere, but it's still made of gas. And when Earth plunges into it, traveling at speeds of dozens of kilometers per second, the friction will be immense. The planet will heat up even further. The surface, already glowing red hot, will begin to boil. Rock will vaporize, creating a tail of gas trailing behind the planet like a comet. The mantle, the thick layer of molten rock beneath the crust, will be exposed. And then it too will start to vaporize. Deeper and deeper the sun will eat into the planet, layer by layer, until it reaches the core. Earth's core is made of iron and nickel, incredibly dense metals that have resisted billions of years of heat and pressure. But even the core can't withstand the temperatures inside the sun. It will melt, it will vaporize, and eventually it will be dispersed into the sun's outer atmosphere, becoming part of the star itself. And that will be the end. The end of Earth as a physical object. The atoms that made up the planet, the iron and oxygen and silicon and all the others, will still exist. They'll be scattered throughout the sun's outer layers. But Earth as a world, as a distinct entity with its own history and identity, will be gone. It's a sobering thought. This planet, which has existed for 4.5 billion years, which has seen the rise and fall of countless species, which has been home to oceans and mountains and forests and cities, will be reduced to a cloud of vapor in the space of a few thousand years. All the complexity, all the beauty, all the history erased. But let's pause here and reflect on what Earth will have accomplished in its lifetime. From its formation 4.5 billion years ago to its destruction 7.5 billion years in the future, Earth will have existed for 12 billion years. That's an extraordinary run for any planet. During that time, it hosted life for at least 3.8 billion years, possibly longer. Life that started as simple single-celled organisms and evolved into an astonishing diversity of forms. Microbes that could survive in boiling water or frozen ice. Plants that transformed the atmosphere, creating the oxygen we breathe. Animals that developed complex behaviors, social structures, intelligence. And eventually, a species that could look up at the stars and ask why. Humans are newcomers to this story. Our species, Homo sapiens, has only existed for about 300,000 years. That's less than 1/100% of Earth's total lifespan. We're a blip on the cosmic timeline. But in that brief moment, we've accomplished remarkable things. We've developed language, allowing us to communicate complex ideas across generations. We've invented writing, preserving knowledge so it can accumulate over time. We've created art, music, literature, philosophy, all the things that make life rich and meaningful. We've developed science, a systematic way of understanding how the world works. We've built cities, connected continents with roads and cables and airways. We've sent spacecraft to other planets, gathering data about worlds we may never visit in person. We've looked deep into space with telescopes, seeing galaxies billions of light years away, peering back in time to the early universe. And we've looked deep into matter with microscopes and particle accelerators, discovering the fundamental building blocks of reality. All of this in just 300,000 years. Imagine what we might accomplish if we survive for another million years, or 10 million, or 100 million. The possibilities are staggering. We could cure all diseases. We could eliminate poverty and hunger. We could build sustainable cities that work in harmony with nature rather than destroying it. We could spread across the solar system, establishing colonies on the Moon, Mars, the asteroid belt, the moons of Jupiter and Saturn. We could mine the resources of other worlds, giving us access to materials and energy on a scale we can barely imagine. We could build megastructures like Dyson spheres that capture all the energy output of the sun, or space elevators that make it trivial to move materials from the surface of Earth into orbit. We could terraform other planets, giving them atmospheres and climates suitable for Earth life. We could engineer ourselves, using genetic modification or cybernetic enhancement, or even mind uploading to overcome our biological limitations. We could create artificial intelligences that help us solve problems and explore possibilities beyond our current comprehension. And if we really think big, we could become an interstellar species, sending ships to other star systems and establishing new civilizations on distant worlds. We could explore the galaxy, meeting other intelligent species if they exist, or spreading life to lifeless worlds if we're alone. We could become part of a galactic community, trading knowledge and resources and culture with civilizations that arose on worlds we've never seen. Or we could be the first, the pioneers who seed the galaxy with life and intelligence, ensuring that even in the far future, long after Earth is gone, the legacy of our world lives on. This is the vision that drives space exploration and astrobiology, the belief that life is too precious to be confined to a single planet, that intelligence is too rare to risk losing, and that the future of life in the universe depends on what we do today. Of course, None of this is guaranteed. We face enormous challenges, both immediate and long-term. Climate change, biodiversity loss, nuclear proliferation, pandemics, resource depletion, social inequality, the list goes on. These are existential risks, threats that could prevent us from ever reaching our full potential. But they're also challenges we can overcome if we choose to. We have the knowledge. We have the technology. What we need is the will, the collective determination to work together, to put aside our differences, to focus on the long term rather than the short term. It won't be easy. It will require sacrifices, compromises, difficult decisions. But the alternative is unthinkable. To squander our potential, to let our species go extinct while we still have the power to prevent it, would be a cosmic tragedy. So let's choose differently. Let's choose to survive. Let's choose to thrive. Let's choose to build a future where our descendants can look back at us and say, they did it. They faced the challenges. They made the tough decisions. And they gave us this incredible gift, the opportunity to live in a world where anything is possible. That's the legacy we can leave. And it starts with the choices we make today. Every action we take, every decision we make, ripples out into the future. When we choose to reduce our carbon footprint, we're helping to stabilize the climate for future generations. When we choose to protect endangered species, we're preserving biodiversity that could one day be essential for our survival. When we choose to invest in education and research, we're building the foundation for future discoveries and innovations. When we choose to be kind, to be compassionate, to help others, we're creating a culture of cooperation that will be essential for tackling the challenges ahead. These choices may seem small in the moment, but they add up, they compound, and over time, they can change the world. This is the power we have as individuals and as a society. We're not powerless in the face of the future. We're the authors of it. We get to decide what happens next. And that's both a tremendous responsibility and an incredible opportunity. So let's embrace it. Let's take ownership of our future. Let's imagine the world we want to create and then work together to make it real. But this is the nature of the universe. Nothing is permanent. Everything changes. Everything ends. And what matters is not how long something lasts, but what it achieves while it exists. After Earth is gone, the sun will continue its evolution. The helium that's been accumulating in the core will eventually ignite, undergoing fusion to form carbon and oxygen. This helium fusion is even more energetic than hydrogen fusion, and it will cause the sun to brighten and expand even further. The sun will become what's called an asymptotic giant branch star, a late-stage red giant that's extremely luminous and unstable. During this phase, the sun will pulsate, expanding and contracting rhythmically. Each pulsation will shed more of its outer layers, creating shells of gas that drift outward into space. These shells will be illuminated by the intense ultraviolet radiation from the sun's exposed core, creating a beautiful glowing nebula. This is called a planetary nebula, though it has nothing to do with planets. The name is a historical artifact from when astronomers first observed these objects through telescopes and thought they looked like planets. Today, we know that planetary nebulae are the death throes of sun-like stars, the final breath before they settle into their ultimate fate. At the center of the planetary nebula, the sun's core will be exposed. It will be a small, incredibly dense object called a white dwarf. A white dwarf is about the size of Earth, but contains about half the mass of the sun. That's an incredible density. A teaspoon of white dwarf material would weigh several tons. The white dwarf is held up not by fusion or by thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain point. This is a stable configuration, and the white dwarf will persist for trillions of years, slowly cooling and fading as it radiates away its residual heat. Eventually, after an incomprehensible span of time, it will cool to the point where it no longer emits visible light. It will become a black dwarf, a cold, dark cinder drifting through space. But the universe isn't old enough for any black dwarfs to exist yet. Even the oldest white dwarfs, which have been cooling for over 10 billion years, are still warm enough to glow faintly. So that's the ultimate fate of the Sun, from a vibrant, life-giving star to a cooling ember, and in the process, it will destroy all the inner planets of the solar system. But the story doesn't end with destruction, because the gas and dust that the Sun sheds during its red giant phase won't just disappear. It will mix with the interstellar medium, the diffuse gas and dust that fills the space between stars. Over millions of years, this material will drift through the galaxy, slowly dispersing, and eventually, some of it will encounter other clouds of gas and dust. These clouds are the birthplaces of stars. When a cloud becomes dense enough, gravity causes it to collapse. As it collapses, it fragments into smaller clumps. Each clump continues to collapse, heating up as gravitational potential energy is converted to thermal energy. Eventually, the center of a clump becomes hot enough to ignite nuclear fusion. A new star is born, and around that star, the remaining gas and dust form a disk, which eventually coalesces into planets. The atoms that were once part of Earth, the carbon that was in the DNA of living organisms, the oxygen that was in the water of the oceans, the silicon that was in the rocks of the crust, all of those atoms could end up in a new star system. They could become part of new planets, and on one of those planets, under the right conditions, life could arise again. It wouldn't be Earth. It wouldn't be the same life, but it would be a continuation of the cosmic story, a new chapter in the endless cycle of creation and destruction. This is the beauty of the universe. Matter and energy are never truly lost. They're recycled over and over in an eternal dance. We are made of stardust, atoms forged in the hearts of ancient stars that exploded billions of years ago. And when the Sun dies, we'll return to the stars, to be reborn as something new. This realization should give us perspective. Our lives, our civilizations, even our planet, are all temporary. We're fleeting patterns in the cosmic flow, here for a moment and then gone. But that doesn't make us insignificant, because while we're here, we have the ability to experience the universe, to understand it, to create beauty and meaning. We can build, we can explore, we can love, we can learn. And those experiences, those moments of connection and discovery and joy, those are real, they matter, even if they don't last forever. In fact, maybe they matter more because they don't last, because they're precious, because they're unique. Every sunset we watch, every conversation we have, every idea we conceive is a one-time event. It will never happen again in exactly the same way, and that makes it valuable. So as we think about the distant future, about the end of Earth and the death of the Sun, let's not be discouraged. Let's be inspired to make the most of the time we have. Inspired to take care of our planet while it's still habitable. Inspired to reach for the stars, to spread life beyond Earth, to ensure that our legacy endures. Because the future is not yet written. We have the power to shape it. We can choose to build a sustainable civilization, one that lasts not just for centuries, but for millennia. We can choose to invest in science and exploration, pushing the boundaries of what's possible. We can choose to work together, to overcome the divisions that separate us, to create a world where everyone has the opportunity to thrive. These choices are in our hands, and the decisions we make today will echo through the ages, affecting not just our own lives, but the lives of countless generations to come. And if we succeed, if humanity survives and thrives and spreads across the galaxy, then the story of Earth will be remembered as the beginning, the place where it all started, the cradle of life, the birthplace of intelligence, the world that gave rise to a civilization capable of reaching the stars. That's a legacy worth fighting for. That's a story worth telling, and it's a future worth building. So let's get to work. Let's take the first steps toward making that future a reality. Let's care for our planet. Let's pursue knowledge. Let's dream big. And let's never give up hope, because the universe is vast and full of possibilities. And we're just getting started. Thank you for joining me on this incredible journey through time and space. We've explored the distant future of our planet, from the gradual brightening of the sun to the collapse of the biosphere, from the evaporation of the oceans to the final destruction of Earth itself. It's been a sobering look at the inevitable end of our world. But it's also been a reminder of the incredible story we're part of. A cosmic tale of creation and destruction, of life and death, of endings and new beginnings. As we close, I want to leave you with one final thought. The universe is over 13 billion years old. It will continue for trillions upon trillions of years. We're living in a very special time, a time when stars are still being born, when planets are still forming, when life still has the opportunity to flourish. This is the stelliferous era, the age of stars, and it won't last forever. Eventually, the universe will run out of hydrogen. Stars will stop forming. The existing stars will burn out, and the universe will enter the degenerate era, a cold, dark age dominated by dead stellar remnants. But we're not there yet. We're here now, in the prime of the universe, and that's something to celebrate. So let's make the most of it. Let's appreciate the beauty of the night sky, the warmth of the sun, the abundance of life on Earth. Let's pursue our curiosity, asking questions and seeking answers about the cosmos and our place in it. Let's create building works of art and engineering that reflect the best of what we're capable of. Let's connect with each other, forming communities and relationships that enrich our lives. And let's dream about the future, imagining the incredible things we might achieve if we work together and refuse to give up. Because the future is ours to shape, and the story we write will be our gift to the cosmos. If you enjoyed this exploration of Earth's distant future, please give this video a like and subscribe to the channel for more deep dives into astronomy, cosmology, and the wonders of the universe. Drop a comment below and let me know what you think. Where are you watching from? What part of this journey resonated most with you? And what other topics would you like to see covered in future videos? Your feedback helps shape the content we create, and I love hearing from you. Until next time, keep looking up, keep asking questions, and keep exploring the infinite mysteries of the cosmos. The universe is waiting. Now, there's another factor we need to consider. The oceans. Oceans aren't just bodies of water. They're massive reservoirs of heat, carbon dioxide, and dissolved minerals. They play a critical role in regulating Earth's climate. As the sun gets brighter, the oceans will start to warm. Warmer oceans hold less dissolved gas, so some of the carbon dioxide currently dissolved in seawater will be released into the atmosphere. That might sound like it would help offset the loss of carbon dioxide due to weathering. And to some extent, it does. But it's not enough. The oceans can only release so much carbon dioxide before they're depleted. And once temperatures get high enough, the oceans themselves start to evaporate. This brings us to the moist greenhouse phase. In a moist greenhouse, the atmosphere becomes saturated with water vapor. Water vapor is a greenhouse gas, and a very effective one. It absorbs infrared radiation, trapping heat close to the surface. The more water vapor in the atmosphere, the warmer the planet gets. And the warmer the planet gets, the more water evaporates from the oceans. It's a positive feedback loop. Once it starts, it's very difficult to stop. On Earth today, the amount of water vapor in the atmosphere is limited by the rate of condensation. When air rises and cools, water vapor condenses into clouds and falls as rain. This keeps the atmosphere from becoming too saturated. But in a moist greenhouse scenario, the entire atmosphere is so hot that condensation becomes less effective. Water vapor accumulates in the lower atmosphere, creating a thick, steamy blanket. The planet's surface gets hotter and hotter. Eventually, the heat becomes so intense that the oceans can't sustain themselves. They evaporate faster than they can be replenished by rainfall. The water cycle breaks down, and the oceans start to shrink. Where does all that water go? Some of it stays in the atmosphere, contributing to the extreme greenhouse effect, but a significant amount escapes into space. Here's how that happens. Water molecules in the upper atmosphere are exposed to intense ultraviolet radiation from the sun. This ultraviolet light has enough energy to break the chemical bonds in water molecules, splitting them into hydrogen and oxygen. The hydrogen atoms, being extremely light, can reach escape velocity and drift off into space. The oxygen atoms either escape as well, carried away by the solar wind, or they react with surface rocks, forming metal oxides. This process is called photodissociation, and it's one of the main ways planets lose their water over geological timescales. We see evidence of this on Venus. Venus likely had oceans early in its history, but it experienced a runaway greenhouse effect. Its proximity to the sun meant it received more solar energy than Earth. The oceans evaporated, water vapor accumulated in the atmosphere, and over time, photodissociation stripped the planet of its water. Today, Venus is bone dry. Its surface is a scorching 460 degrees Celsius, hot enough to melt lead. Its atmosphere is dominated by carbon dioxide, with crushing surface pressures 90 times greater than Earth's. This is Earth's future. In about 1 billion years, we'll enter the moist greenhouse phase. Within a few 100 million years after that, the oceans will be gone. And by 2 billion years, Earth will look a lot like Venus does today. But there's one more twist to this story. Plate tectonics. Plate tectonics is the engine that drives much of Earth's geological activity. It's responsible for earthquakes, volcanoes, mountain building, and the recycling of the crust. And it's powered by heat from Earth's interior. But plate tectonics also depends on water. Water acts as a lubricant, allowing the tectonic plates to slide past each other more easily. It lowers the melting point of rocks in the mantle, making it easier for magma to form and rise to the surface. Without water, plate tectonics becomes much more difficult. As Earth loses its oceans, the crust will dry out. The rocks will become more brittle. Subduction, the process where one tectonic plate is pushed beneath another, will slow down. Eventually, it will stop altogether. And when subduction stops, the carbonate-silicate cycle stops too. No more carbonate rocks being pulled into the mantle. No more carbon dioxide being released by volcanic outgassing. The planet's geological activity will grind to a halt. With no active plate tectonics, the surface of the planet will change much more slowly. There will still be some geological activity. Hotspots in the mantle, like the one that created the Hawaiian Islands, will continue to produce shield volcanoes. These volcanoes will release small amounts of carbon dioxide and other gases, slowly building up the atmosphere. But without the recycling provided by plate tectonics, the crust will become more and more stagnant. Impact craters, which on Earth today are eroded away relatively quickly, will accumulate. The surface will start to resemble that of Mars or the Moon, pockmarked and ancient. Now, let's fast forward even further. 2.8 billion years from now, all life on Earth is extinct, but the planet itself is still there, still orbiting the Sun. What happens next? For the next few billion years, Earth will continue to be heated by the ever-brightening Sun. The surface temperature will climb higher and higher. By 4 billion years from now, the temperature could reach 400 degrees Celsius or more. The atmosphere will be thick and heavy, dominated by carbon dioxide and nitrogen, with remnants of water vapor in the upper layers. The surface pressure will be immense, many times what it is today. The rocks on the surface will be heated to the point where some of them start to glow. And in the hottest regions, the rock will begin to melt. Lava pools will form, not from volcanic eruptions, but purely from the heat of the sun. This is what scientists call a runaway greenhouse effect. Once it starts, there's no going back. The planet is locked into a feedback loop of ever-increasing temperatures. The only thing that could stop it is if the sun's luminosity were to suddenly drop. But that's not going to happen. The sun will continue to brighten for billions of years to come. And then, about 6 billion years from now, the sun will begin its transformation into a red giant. This is the final act. The sun has been burning hydrogen in its core for over 10 billion years by this point. But now, the hydrogen is running out. The core, composed mostly of helium, will start to contract under its own gravity. As it contracts, it heats up. Eventually, it will get hot enough to ignite helium fusion. But before that happens, hydrogen fusion will ignite in a shell around the core. This shell fusion releases enormous amounts of energy, pushing the outer layers of the sun outward. The sun begins to expand. At first, the expansion is gradual. The sun swells from a main sequence star into a subgiant. Its luminosity increases. Its surface cools slightly, shifting from yellow to orange. Earth, still orbiting at roughly its current distance, is blasted by ever-increasing amounts of radiation. The surface temperature soars. Any remaining atmosphere is stripped away by the intense solar wind. The planet becomes a lifeless, molten ball of rock. As the sun continues to expand, it becomes a red giant. Its outer layers stretch out to encompass the inner planets. Mercury is the first to go, swallowed by the sun's expanding envelope. Then Venus, and then most likely, Earth. The exact fate of Earth depends on how much mass the sun loses during its red giant phase. As the sun sheds its outer layers, its gravitational pull on the planets weakens. This causes their orbits to expand slightly. Some models suggest that Earth's orbit could expand enough to avoid being engulfed, but the most recent studies indicate that this is unlikely. The sun's outer atmosphere will reach Earth's orbit. The planet will find itself inside the sun. The friction will cause its orbit to decay. It will spiral inward, closer and closer to the sun's core, and eventually it will be torn apart. The surface will vaporize. The crust will boil away. The mantle and core will be heated until they too disintegrate. Earth will be reduced to a cloud of gas and dust, dispersed throughout the sun's outer layers. This is the ultimate fate of our planet. Not a quick, violent end like an asteroid impact, but a slow, inevitable death by fire. It's a fate determined by the nature of stars and the laws of physics. And it's a fate that awaits all planets orbiting sun-like stars. But here's the thing. Even though Earth will be destroyed, the atoms that made up our planet won't disappear. They can't. The law of conservation of mass tells us that matter can't be created or destroyed, only transformed. The iron that once formed Earth's core, the silicon and oxygen that made up its crust, the carbon and nitrogen that were part of living organisms, all of those atoms will be scattered into space when the sun sheds its outer layers. They'll become part of a planetary nebula, a glowing cloud of gas and dust. Over time, that cloud will drift through the galaxy, mixing with other nebulae, colliding with clouds of interstellar gas, and eventually, some of that material will collapse under its own gravity to form a new star. That new star might have planets, and on one of those planets, under the right conditions, life might arise again. The atoms that were once part of you, of me, of every living thing on Earth, could become part of new worlds, new forests, new oceans, new civilizations. This is the beauty of the cosmos. Nothing is ever truly lost. It's all recycled over and over in an endless cycle of creation and destruction. We are literally made of stardust, atoms forged in the hearts of ancient stars that exploded billions of years ago. And when our sun dies, we'll return to the stars, to be reborn as something new. So, what does all of this mean for us, right now, in the present? It means that time is precious. Earth won't be habitable forever. We have, at most, 1 billion years before the planet becomes too hot for complex life. That might sound like a long time. And in human terms, it is. 1 billion years is an almost incomprehensible span of time. But in cosmic terms, it's the blink of an eye. Our sun is middle-aged. It's been burning for 4.5 billion years, and it has another 5 billion years to go before it becomes a red giant. Earth's remaining habitability is a fraction of the sun's total lifespan. We're living in a golden age, a brief window of time when the conditions are just right for life to flourish. That window will close, and when it does, it won't reopen. So what should we do with the time we have? That's a question each of us has to answer for ourselves. But I think there's something profound in recognizing the impermanence of our world. It makes the present moment more valuable. It reminds us to appreciate what we have, to take care of our planet, to explore, to learn, to create, to connect with each other. Because this is our one chance. This is the time we've been given, and we won't get another. If humanity survives for the next few million years, we'll have to make some big decisions. Do we try to save Earth? Do we engineer solutions to keep the planet habitable, even as the sun brightens? Or do we accept the inevitable and focus on spreading life to other worlds? Both paths are possible. Both have their challenges. Saving Earth would require technologies we can barely imagine today. We'd need to control the planet's climate at a global scale. We'd need to replenish the oceans, regulate atmospheric carbon dioxide, maybe even shield the planet from excess solar radiation. Some scientists have proposed using solar shades, massive structures in space that block a portion of the sun's light before it reaches Earth. Others have suggested geoengineering the atmosphere, injecting aerosols or other particles to reflect sunlight back into space. These ideas sound like science fiction, but they're based on real physics. And if we have millions of years to develop the technology, who knows what we might achieve? The other option is to leave, to become a spacefaring civilization, spreading life beyond Earth. We've already taken the first steps in this direction. We've sent humans to the moon. We've landed rovers on Mars. We've sent probes to the outer planets and beyond. We're learning how to live in space, how to grow food in microgravity, how to recycle air and water. These are baby steps, but they're important. If we can establish permanent colonies on Mars or in orbit around Earth, or on the moons of Jupiter and Saturn, we'll have a backup, a way to ensure that even if Earth becomes uninhabitable, humanity survives. And if we really want to think long-term, we could consider interstellar travel. There are hundreds of billions of stars in our galaxy. Many of them have planets. Some of those planets are likely to be habitable. If we could build spacecraft capable of traveling between the stars, we could colonize other solar systems. We could spread life throughout the galaxy. It's an audacious vision, but it's not impossible. The distances are vast, yes. The nearest star system, Alpha Centauri, is over 4 light-years away. With our current technology, it would take tens of thousands of years to get there. But technology improves. Concepts like nuclear pulse propulsion, fusion drives, or even theoretical ideas like warp drives could make interstellar travel feasible within a few centuries. If we survive long enough, we might become a truly galactic species. And if we do, the story of Earth will be just the beginning. Our home planet will be remembered as the cradle of humanity, the place where it all started. But it won't be the end. It will be the first chapter in a much larger story. Of course, none of this is guaranteed. We might not survive the next few centuries, let alone the next billion years. Climate change, nuclear war, pandemics, asteroid impacts. There are plenty of ways humanity could be wiped out long before the sun becomes a threat. But that's all the more reason to value the time we have, to work together, to solve the problems we face today, to build a future where our descendants can look back and say, we made it, we survived, we thrived, and we became something greater than we ever imagined. That's the challenge, and it's a challenge worth taking on. Because the alternative, extinction, is not an option we should accept willingly. We owe it to ourselves, to our children, and to all the generations that will come after us to fight for a future, to explore, to learn, to grow, to become the best version of ourselves that we can be. So here we are, standing on a small blue planet, orbiting an average star in an unremarkable corner of the galaxy. But what we do here matters. The choices we make, the lives we live, the legacy we leave behind, all of it matters. Because we're part of the story of the universe, a story that began with the Big Bang 14 billion years ago and will continue for trillions of years to come. We're a tiny part of that story, yes, but we're a part nonetheless, and that's something worth celebrating. As we wrap up this journey through Earth's distant future, let's take a moment to reflect on what we've learned. We've seen how the brightening sun will trigger a cascade of changes on our planet, how the carbonate silicate cycle will break down, pulling carbon dioxide from the atmosphere and starving the plants, how the biosphere will collapse from complex animals to simple microbes until all life is extinguished, how the oceans will evaporate and escape into space, leaving behind a dry, barren wasteland, how the planet's geology will change with tectonic activity grinding to a halt and the surface becoming a cratered ancient landscape, how temperatures will soar to hundreds of degrees, turning the surface into a molten hellscape, and how, finally, Earth will be swallowed by the sun as it expands into a red giant, erasing all trace of the world that once was. It's a sobering vision, but it's also a reminder of the incredible journey this planet has been on. 4.5 billion years ago, Earth was a ball of molten rock, bombarded by asteroids and comets, with no atmosphere, no oceans, no life. Over hundreds of millions of years it cooled. Water condensed from the steam in the atmosphere, forming the first oceans. The crust solidified, and somewhere in those ancient seas, life began. Simple single-celled organisms that could harness energy from their environment. Over the next few billion years, life evolved. It became more complex. It adapted to new environments. It survived mass extinctions, ice ages, volcanic eruptions, asteroid impacts. It filled every corner of the planet, from the deepest ocean trenches to the highest mountain peaks. And eventually, it gave rise to us, humans, intelligent, curious, creative beings capable of understanding the cosmos and our place in it. We're the result of billions of years of evolution, of countless generations of organisms that lived, reproduced, and died, each one passing on its genes to the next. We're the culmination of an incredible story, and we have the unique privilege of being able to tell that story, to look back at the history of life on Earth, to understand how we got here, and to look forward, to imagine what might come next. But the story of Earth isn't just about the past and the future. It's about the present. Right now, in this moment, Earth is alive. It's a vibrant, dynamic, beautiful world. The oceans are full of life. From microscopic plankton to giant whales, the forests are teeming with animals, insects, birds, plants. The atmosphere is breathable. The climate, for now, is relatively stable. We have liquid water, blue skies, sunsets, seasons. We have all the things that make Earth unique in the solar system, and possibly in the galaxy. This is our home, and it's a home worth protecting, because even though the sun will eventually make Earth uninhabitable, that's billions of years away. The threats we face today, climate change, habitat destruction, pollution, loss of biodiversity, these are things we can do something about. We have the knowledge, the technology, and the ability to make a difference. All we need is the will. So let's not waste this opportunity. Let's take care of our planet. Let's preserve the incredible diversity of life that makes Earth so special. Let's work together to build a sustainable future, one where humanity can thrive alongside the natural world, rather than at its expense, because the time we have on this planet is precious, and we owe it to ourselves and to all the other species we share this world with to make the most of it. And as we look to the future, let's dream big. Let's imagine a world where we've solved the challenges we face today, where we've transitioned to clean energy, where we've restored ecosystems, where we've learned to live in harmony with nature. Let's imagine a future where we've ventured beyond Earth, where we've established colonies on other planets, where we've sent spacecraft to explore distant star systems. Let's imagine a future where humanity has become a truly interstellar species, spreading life and intelligence throughout the galaxy. It's an ambitious vision, but it's not impossible. All the great achievements in human history, from the invention of the wheel to the landing on the moon, started with someone daring to dream, someone imagining a future that didn't yet exist, and then working to make it real. We have that same power. We can shape the future. We can decide what kind of world we want to leave for the generations that come after us. And we can start right now, today, by making choices that reflect the kind of future we want to see. So what have we learned from this journey? We've learned that nothing lasts forever, that Earth, like all planets, has a beginning, a middle, and an end. We've learned that the sun, our source of light and warmth, will one day become our destroyer. We've learned that life is resilient, but it's not invincible. And we've learned that the time we have is precious. But we've also learned something else. We've learned that we're part of something much bigger than ourselves. We're part of the cosmic cycle of creation and destruction. We're made of atoms that were forged in the hearts of stars. And when we die, those atoms will live on, becoming part of new worlds, new stars, new forms of life. We're connected to the universe in a way that's both humbling and awe-inspiring. And that connection gives our lives meaning, even in the face of our own mortality and the eventual demise of our planet. And that brings us to the end of our story. The story of Earth, 1 billion years from now, is a story of change, of loss, of endings. But it's also a story of resilience, of transformation, of new beginnings. Because even as one chapter closes, another opens. The atoms that make up our world will be scattered to the stars to be reborn as something new. And the legacy of life on Earth, the knowledge we've gained, the art we've created, the love we've shared, all of that will live on in the memories of those who come after us. Or, if humanity survives long enough, in the civilizations we build on other worlds. The story doesn't end, it just changes. And that's the beauty of it. So as we close this video, let's take a moment to appreciate the world we have right now. Let's look up at the blue sky, feel the warmth of the sun on our skin, listen to the sound of the wind in the trees. Let's remember that we're living in a golden age, a brief window of time when Earth is at its most beautiful. And let's make the most of it, because one day, billions of years from now, this will all be gone. But until then, this is our home, and it's a home worth celebrating. Looking deeper into the timeline of Earth's transformation, we need to understand the mechanics of how plate tectonics will change over the coming hundreds of millions of years. Right now, Earth's plates are moving at rates of a few centimeters per year. The Pacific plate is sliding beneath the North American plate, creating the volcanoes of the Cascade Range. The Indian plate is colliding with the Eurasian plate, pushing up the Himalayas. The Atlantic Ocean is widening as the mid-Atlantic ridge spreads, pulling the Americas away from Europe and Africa. These movements are driven by convection currents in the mantle, the thick layer of hot rock beneath the crust. Heat from Earth's core and from radioactive decay warms the mantle, causing it to flow in massive circular patterns. Hot material rises, spreads out beneath the crust, cools, and sinks back down. This convection is what drives the plates. But over the next few 100 million years, the pattern of plate movement will change. The Atlantic Ocean, which has been widening for the past 200 million years, will eventually start to close again. The Pacific Ocean, currently the largest body of water on Earth, will shrink, and the continents will drift toward each other, eventually colliding to form a new supercontinent. This isn't the first time this has happened. Earth has gone through several cycles of supercontinent formation and breakup. The most recent supercontinent was Pangaea, which existed about 300 million years ago. Before that, there was Rodinia, which formed about 1 billion years ago. And before that, there were others whose names we don't even know. This is called the supercontinent cycle, and it repeats roughly every 400 to 600 million years. The next supercontinent, which some scientists have named Pangaea Proxima, is expected to form in about 250 million years. Based on current plate motions, Africa and Europe will collide, closing the Mediterranean Sea. The Americas will drift back toward Africa and Europe, closing much of the Atlantic. Australia will continue its northward journey, eventually colliding with Southeast Asia. The result will be a massive landmass, ringed by a global ocean. But this supercontinent will be very different from Pangaea. Pangaea existed during a time when Earth's climate was relatively stable, when plants and animals were abundant. Pangaea Proxima will form during a time of climate crisis. The sun will be several percent brighter than it is today. Atmospheric carbon dioxide levels will be dropping. Plant life will already be in decline. The formation of the supercontinent will make things worse. When all the land is clustered together, the interior of the continent is far from any ocean. This creates a hyper-arid climate. Today, we can see this effect in the interior of large continents like Asia and Australia, where deserts dominate. But with Pangaea Proxima, the effect will be extreme. The center of the continent could be over 1,000 kilometers from the nearest coast. Without the moderating influence of ocean water, temperatures will swing wildly between day and night, between summer and winter. Daytime temperatures in the interior could reach 60 or even 70 degrees Celsius. Nighttime temperatures might drop to freezing. It will be a brutal environment, hostile to almost all forms of life. The coastlines, meanwhile, will experience their own problems. The global ocean surrounding the supercontinent will have powerful currents, driven by the temperature difference between the equator and the poles. These currents will create massive storm systems, hurricanes and cyclones far more powerful than anything we see today. Coastal regions will be battered by relentless winds and waves. And because the ocean will be warmer than today's oceans, the storms will carry enormous amounts of moisture. When they make landfall, they'll dump that moisture in torrential downpours, causing catastrophic flooding. The contrast between the wet coastlines and the dry interior will be stark. It will be a planet of extremes, with no middle ground. And for life, already struggling with the loss of atmospheric carbon dioxide and rising temperatures, it will be one more challenge to overcome. Now, let's talk about what happens to the atmosphere over these timescales. Today, Earth's atmosphere is composed mostly of nitrogen and oxygen, with trace amounts of carbon dioxide, water vapor, and other gases. The oxygen is there because of photosynthesis. Plants and photosynthetic bacteria produce oxygen as a byproduct of converting carbon dioxide and water into sugars. Over billions of years, this process has gradually built up the oxygen in our atmosphere from nearly 0 to the 21% we have today. But when plants disappear, oxygen production stops, and oxygen is a reactive gas. It doesn't just sit in the atmosphere doing nothing. It reacts with rocks, with metals, with organic matter. Over time, these reactions will consume the oxygen, pulling it out of the atmosphere and locking it away in oxidized minerals. The process is slow, but it's steady. Within a few tens of millions of years after plants disappear, atmospheric oxygen levels will start to drop. Within 100 million years, they could fall to just a fraction of what they are today. For animals, this would be catastrophic even if they had enough food. Oxygen is essential for respiration, the process by which animals extract energy from food. As oxygen levels drop, animals would struggle to breathe. They would become lethargic, unable to move or hunt effectively. Eventually, they would suffocate. But as we've already discussed, by the time oxygen levels drop significantly, most animals will already be gone, starved to death by the collapse of the plant kingdom. The real significance of the oxygen decline is what it means for the planet's chemistry. Oxygen is what we call an oxidizing agent. It reacts with reduced compounds, breaking them down. Without oxygen, the chemistry of the atmosphere and the surface will shift. Reduced gases like methane and hydrogen sulfide, which are currently rare because they react with oxygen, could start to build up. The atmosphere could take on a different composition, one that's more similar to what Earth had billions of years ago, before the rise of photosynthetic organisms. This is sometimes called a return to the Archean. named after the geological eon that lasted from about 4 billion to 2.5 billion years ago. During the Archean, Earth's atmosphere had almost no oxygen. It was dominated by nitrogen, carbon dioxide, and methane. The surface was covered in shallow seas. Life existed, but it was simple. Just single-celled bacteria and archaea. There were no animals, no plants, no fungi. Just microbes living in the water and in the mud. And in about 1 billion years, Earth could return to something similar. A world without oxygen, without complex life, dominated by microbes. Except this time, the temperature will be much higher. The Archean Earth was relatively cool, thanks to the dimmer sun. The future Earth will be hot, scorched by a sun that's 10% brighter. The microbes that survive will have to be extremophiles, organisms adapted to extreme heat, extreme salinity, extreme acidity. They'll live in the few remaining pockets of moisture, in deep caves, in underground aquifers, in the cracks of rocks where water might condense briefly before evaporating again. They'll be hanging on by a thread. And speaking of extremophiles, let's take a closer look at what kinds of organisms might be the last to go. Today, Earth is home to a remarkable diversity of extremophiles, organisms that thrive in conditions that would kill most other forms of life. There are thermophils, which live in hot springs and hydrothermal vents at temperatures above 80 degrees Celsius. There are halophils, which live in salt lakes and salt pans, where the salinity is 10 times higher than seawater. There are acidophils, which live in acidic environments with pH values as low as 0. There are psychrophils, which live in the freezing temperatures of Antarctica. And there are organisms called polyextremophils, which can tolerate multiple extreme conditions at once. These extremophils give us a window into what the last survivors on Earth might look like. They'll be small, probably single-celled. They'll have specialized proteins and membranes that can withstand high temperatures without breaking down. They'll have mechanisms to deal with dehydration, allowing them to go dormant when water isn't available and spring back to life when it returns. They'll have DNA repair mechanisms to fix the damage caused by intense ultraviolet radiation. And they'll have metabolisms that can extract energy from sources other than sunlight. Because once plants are gone, photosynthesis won't be an option. The remaining microbes will need to rely on chemosynthesis, a process where energy is extracted from chemical reactions rather than from sunlight. We see this today in deep-sea hydrothermal vents, where bacteria use the chemical energy from hydrogen sulfide and other compounds spewing out of the vents. On future Earth, chemosynthetic microbes might live deep underground, where radioactive decay in the rocks provides a slow but steady source of energy. Or they might live in areas where volcanic gases are still being released, using those gases as an energy source. They'll be living on the edge, eking out an existence in a world that's becoming increasingly hostile. But they'll survive for a while, until the heat becomes too much. Until even the deepest caves and the most sheltered cracks in the rocks can't provide refuge from the relentless sun. And then they too will die, and Earth will be lifeless. Let's think about what that means. A lifeless Earth. No birds singing in the trees. No fish swimming in the oceans. No insects buzzing in the air. No bacteria in the soil. Nothing. Just rock and sand and dust, baking under an unforgiving sun. It's a haunting image, and it's made even more poignant when you think about everything that came before. Earth has been a living planet for at least 3.8 billion years, maybe longer. In that time, life has evolved from simple single-celled organisms into an astonishing array of forms. Trilobites and dinosaurs, ferns and flowering plants, bacteria that can survive in boiling water and fungi that stretch for kilometers underground, blue whales and hummingbirds, humans and our closest relatives, the great apes. All of this diversity, all of this complexity, arose from a single common ancestor, a microbe that lived billions of years ago, and all of it will eventually disappear, erased by the changing conditions on our planet. But here's the thing, even though life on Earth will end, the story of life itself doesn't have to. If humans, or our descendants, or whatever intelligent species arises after us, can spread life to other worlds, then the story continues. We could terraform Mars, giving it a thicker atmosphere, warming it up, melting its frozen water, and introducing plants and microbes to create an ecosystem. We could build habitats on the moons of Jupiter and Saturn, enclosed environments where life could flourish, protected from the harsh conditions outside. We could send generation ships to other star systems, carrying frozen embryos or seeds or digital blueprints for organisms, ready to be brought to life when we arrive at a new world. This is the dream of astrobiology and space exploration, not just to study life but to spread it, to ensure that even if Earth becomes uninhabitable, life persists elsewhere. It's a grand vision, one that will require technology we haven't yet developed and resources we haven't yet gathered. But it's not impossible. And if we're thinking on timescales of millions or billions of years, we have time to figure it out. Of course, that assumes we survive the next few centuries. Right now, humanity is facing some serious challenges. Climate change is already causing temperatures to rise, sea levels to climb, and weather patterns to shift. If we don't get it under control, it could lead to widespread famine, displacement, and conflict. We're also dealing with biodiversity loss, as habitats are destroyed and species go extinct at rates not seen since the last mass extinction 66 million years ago. We have nuclear weapons, enough to wipe out most of humanity in a matter of hours. We have pandemics, like the one we experienced recently, which reminded us how vulnerable we are to infectious diseases. And we have the ever-present threat of asteroid impacts, though thankfully, we're getting better at detecting and potentially deflecting dangerous space rocks. These are all near-term threats, things that could happen in our lifetimes or the lifetimes of our children. They're much more immediate than the sun brightening over the next billion years, and they're the things we need to focus on if we want to survive long enough to face those distant challenges. But let's assume, for the sake of argument, that we do survive, that we solve climate change, that we protect biodiversity, that we avoid nuclear war and pandemics and asteroid impacts. What then? What does a future look like where humanity has made it through the next few thousand years, the next few million years, intact? It's hard to say, because so much will change. Technology will advance in ways we can't even imagine. Our understanding of physics, of biology, of the universe will deepen. We might discover new forms of energy, new ways to manipulate matter, new methods of communication and transportation. We might even unlock the secrets of consciousness, of intelligence, of what it means to be alive. And with those advances, we might develop the ability to do things that seem like magic to us today, like moving entire planets, like building megastructures that harness the energy of stars, like creating artificial intelligences that surpass human intelligence by orders of magnitude. These are the kinds of things that advanced civilizations, if they exist, might be capable of. And if we become one of those advanced civilizations, then the fate of Earth, as I've described it, isn't set in stone. We could intervene. We could find ways to keep the planet habitable even as the sun brightens. One idea is to use something called a solar shade. Imagine a massive structure positioned between Earth and the Sun that blocks a small percentage of the Sun's light. It wouldn't have to block much. Just a few percent would be enough to offset the increased luminosity of the Sun and keep Earth's temperature stable. The challenge is building something that large and keeping it in position. It would have to be in a stable orbit, constantly adjusting to stay between the Sun and Earth. But with advanced enough technology, it's possible. Another idea is to move Earth's orbit. As the Sun gets brighter, we could slowly nudge the planet outward, keeping it in the habitable zone. This sounds crazy, but it's actually been seriously proposed by scientists. The idea is to use gravitational assist from asteroids. You'd redirect a large asteroid so that it passes close to Earth, transferring some of its momentum to the planet. Do this enough times with enough asteroids, and you could gradually shift Earth's orbit. It would take thousands or millions of years, but we'd have that much time. A third idea is atmospheric engineering. If we can control the composition of Earth's atmosphere, we can control its temperature. Want to cool the planet down? Remove greenhouse gases, or add reflective aerosols that bounce sunlight back into space. Want to warm it up? Add greenhouse gases. This is essentially geoengineering on a planetary scale, and it's something we're already starting to think about in the context of climate change. In the future, with better technology and better understanding, we might be able to fine-tune the atmosphere to keep the planet at exactly the right temperature, no matter how bright the Sun gets. Of course, all of these ideas come with risks. What if the solar shade malfunctions? What if moving Earth's orbit goes wrong and we end up on a collision course with another planet? What if our atmospheric engineering has unintended side effects? These are valid concerns, but they're also the kinds of problems that an advanced civilization would need to solve. And if we're thinking on timescales of millions or billions of years, we'll have plenty of time to test, refine, and perfect these technologies. But even with all of this, there's a limit. Eventually, the Sun will become a red giant. And when that happens, no amount of engineering will save Earth. The planet will be too close to the expanding Sun. It will be engulfed. So if humanity or our descendants want to survive that far into the future, we'll need to leave. We'll need to find new homes among the stars. And that brings us back to the idea of interstellar travel. Traveling to another star system is one of the greatest challenges we could ever undertake. The distances are staggering. The nearest star, Proxima Centauri, is 4.2 light-years away. That's about 40 trillion kilometers. With our current fastest spacecraft, it would take over 70,000 years to get there. We need to go faster, much faster. And to do that, we need new propulsion systems. One possibility is nuclear pulse propulsion, where a spacecraft is propelled by detonating nuclear bombs behind it. The explosions push the craft forward. It sounds insane, but it was actually seriously studied in the 1960s under a project called Orion. The calculations showed that it could work, and that it could accelerate a spacecraft to a significant fraction of the speed of light. Another possibility is fusion drives, which use the energy from nuclear fusion reactions to propel the spacecraft. Fusion is the same process that powers the Sun, and it releases enormous amounts of energy. If we can harness that energy for propulsion, we could build spacecraft that are much faster and more efficient than anything we have today. There are even more speculative ideas, like antimatter drives. Antimatter is matter composed of antiparticles, which have the opposite charge of normal particles. When matter and antimatter meet, they annihilate each other, converting all of their mass into energy according to Einstein's famous equation, E equals mc squared. The amount of energy released is enormous. A single gram of antimatter annihilating with a gram of matter would release as much energy as a nuclear bomb. If we could produce and store antimatter and use it to power a spacecraft, we could achieve speeds close to the speed of light. The problem is that antimatter is incredibly difficult to produce and even harder to store. We can make tiny amounts of it in particle accelerators, but we're talking about a few atoms at a time. Scaling that up to the quantities needed for interstellar travel is a huge challenge, but it's not impossible. With enough time and resources, it could be done. And then there are the really wild ideas like warp drives. A warp drive would bend space-time around the spacecraft, allowing it to travel faster than light without actually violating the laws of physics. The spacecraft would sit inside a bubble of normal space-time, while the bubble itself moves through space faster than light. It's a concept that comes from Einstein's theory of general relativity, and it's mathematically possible. But there are enormous practical challenges. It would require exotic matter, a type of matter with negative mass, which we've never observed and aren't even sure exists. And the energy requirements would be astronomical, possibly more than the total energy output of a star. So while warp drives are fun to think about, they're probably not something we'll be building anytime soon. But even without warp drives, we could still reach other star systems using more conventional technology. It would just take a long time. One approach is the generation ship, a massive spacecraft designed to support a population of humans for thousands of years. The original crew would launch the ship, but they'd never reach the destination. Their children would be born on the ship, live their entire lives in space, and have children of their own. This would continue for dozens or hundreds of generations until finally, thousands of years later, the descendants of the original crew would arrive at their destination. It's a daunting concept, both technologically and socially. The ship would need to be completely self-sufficient, recycling air and water, growing food, repairing itself. It would need to protect the inhabitants from cosmic radiation, from micrometeoroids, from the psychological challenges of living in a confined space for their entire lives. And it would need to maintain the knowledge and skills necessary to colonize a new world when they finally arrive. But if we can solve those challenges, generation ships could be our ticket to the stars. Another approach is the seed ship. Instead of carrying living humans, a seed ship would carry frozen embryos, or even just digital information, the blueprints for building humans and other organisms. The ship would travel to a distant star system, and when it arrived, automated systems would build habitats, warm up the embryos, and raise the first generation of colonists. This has some advantages over generation ships. Frozen embryos don't need food or water or air during the journey. They don't get bored or have mental health issues. And a seed ship could be much smaller and lighter than a generation ship, making it easier to accelerate to high speeds. The downside is that you'd need very sophisticated artificial intelligence to run the ship and raise the first generation of humans. And there are ethical questions about creating humans who never chose to be part of this mission. But it's an option worth considering. And then there's the idea of uploading our minds. If we could scan a human brain, capture all of its information, and upload that information to a computer, we could send digital copies of ourselves to other star systems. These digital minds would travel as data, transmitted via laser or radio signals at the speed of light. When the signal reaches its destination, the information could be downloaded into a new body, either biological or robotic. This would allow us to explore the galaxy without the need for physical spacecraft. We just beam ourselves across space as pure information. Of course, this raises all sorts of philosophical questions about identity and consciousness. If you upload your mind, is the digital copy really you? Or is it just a copy, while the original you stays behind? These are questions we'd need to grapple with before we could seriously pursue this approach. But if we can solve the technical and ethical challenges, mind uploading could make interstellar colonization much easier. No matter which approach we take, the important thing is that we start thinking about it now. Interstellar travel is a multi-generational project. It's something that will take centuries or millennia to achieve. But if we start laying the groundwork today, researching the technologies, solving the problems, training the people, then future generations will have the tools they need to make it happen. And if we do succeed, if humanity becomes a multi-planet, multi-star species, then our story will continue long after Earth is gone. We'll carry the legacy of our home planet with us, preserving the knowledge, the culture, the genetic information, the memory of what Earth once was. And on new worlds, orbiting distant stars, we'll build new civilizations. We'll continue to explore, to learn, to grow. And the story of life, which began in the oceans of Earth billions of years ago, will spread throughout the galaxy. Now, let's return to Earth one last time and think about what we've learned. We've traveled forward in time, watching as the sun brightens, as the climate changes, as life struggles and ultimately fails to adapt. We've seen the oceans evaporate, the continents merge and crack, the atmosphere transform. We've witnessed the end of complex life, the extinction of the last microbes, and the slow transformation of Earth into a lifeless, molten world. It's a grim vision, but it's also a realistic one. This is what the laws of physics predict will happen to our planet, and while it's billions of years away, it's worth thinking about. Because it reminds us that our time here is finite, that the Earth we know and love won't last forever, and that we have a responsibility to make the most of the time we have. So what can we do? How should we live our lives in the face of this knowledge? I think the answer is simple. We should live with gratitude. Gratitude for the fact that we're here at all, that we get to experience this incredible planet in its prime. Gratitude for the beauty of nature, for the warmth of the sun, for the sound of rain, for the company of other people. We should live with curiosity. We should keep asking questions, keep exploring, keep learning about the universe and our place in it. Because the more we understand, the better equipped we are to face the challenges ahead. We should live with compassion. We should care for each other, for the other species we share this planet with, for the generations that will come after us, because we're all in this together, and we have a shared responsibility to protect our home and build a future where life can thrive. And we should live with hope. Hope that we can solve the problems we face today. Hope that we can build a sustainable civilization that lasts not just for centuries, but for millennia. Hope that we can one day spread life to other worlds, ensuring that the story continues long after Earth is gone. This hope isn't naive. It's grounded in the incredible achievements of humanity so far. We've gone from living in caves to building cities, from hunting and gathering to farming and industry, from walking on 2 feet to flying through the air and traveling to space. We've cured diseases, split the atom, decoded the human genome, and sent spacecraft to the edge of the solar system. We've achieved things our ancestors could never have imagined. And if we can keep that spirit of innovation and exploration alive, there's no telling what we might achieve in the future. So yes, Earth will one day be destroyed, the sun will expand, the planet will be engulfed, and everything we know will be gone. But that's not the end of the story, because the atoms that make up our world, the knowledge we've gained, the legacy of life on Earth, all of that will live on. It will be scattered to the stars, to be reborn in new forms, in new worlds, in new chapters of the cosmic story. And if we do our part, if we take care of our planet, if we build a sustainable future, if we spread life beyond Earth, then our descendants will be there to see it. They'll look back at us, at the people who lived in the 21st century, and they'll remember us as the generation that made it possible. The generation that chose to dream big, to work hard, to overcome the challenges we faced. The generation that ensured the survival of life, not just on Earth, but throughout the galaxy. That's the legacy we can leave. That's the impact we can have. And it starts right now with the choices we make today. So let's make them count. Let's take care of our planet. Let's invest in science and education. Let's work together to solve the challenges of climate change, biodiversity loss, and inequality. Let's dream big about the future, about the kind of world we want to build, about the kind of species we want to become. And let's take the first steps toward making those dreams a reality, because the future is ours to shape. And if we're bold enough, brave enough, and wise enough, we can make it extraordinary. We can ensure that the story of life which began on this small blue planet continues for billions of years to come, spreading throughout the cosmos, touching worlds we can only imagine. That's the challenge, that's the opportunity, and it's one we can't afford to pass up. Thank you for joining me on this journey through time. If you enjoyed this video, please consider liking and subscribing to the channel. Your support helps us create more content like this, exploring the wonders of the universe and the incredible story of our planet. Leave a comment below and let me know where you're watching from. I'd love to hear from you. And until next time, keep looking up at the stars, keep asking questions, and keep dreaming about the future. Because the future is ours to shape, and together we can make it extraordinary.